Okay, is it on now? Okay, good. Well, so I will now tell you about Mossbauer spectroscopy. I had originally intended to be approximately 1 minute on stage to introduce my friend and mentor, Eckhard Bill. But as it so turns out, Eckhard could not come, unfortunately, because he was actually doing some travel that prevented him from getting a visa here. And so, unfortunately, he cannot be here. We hatched this plan out before then, probably in the last summer. And this is us actually at the 2015 Mossbauer conference where we met after a long time. This is Eckhard Bill, Bernd Mienert from the Max Planck Institute, Mossbauer technician. And at the Max Planck Institute, we all met for the first time. That was in late 1994, early 1995. I was a grad student with Karl Wiechert, first generation at the Max Planck. Eckhard was just hired there as the super-duper know-it-all physicist and who can teach the chemists spin Hamiltonians and Mossbauer and API, and I knew nothing about this when I came there. And everything I know about spin Hamiltonians and Mossbauer and API can be traced back to Eckhard. I think there would be no better person to do this perhaps. And I got a lot of comments when it became clear that Eckhard couldn't come. I had the full support of the group. You are going to give the Mossbauer lecture. Eckhard can't be replaced, and it's true. So I'll try my best. So I have here a little bit of recommended literature. The book that Eckhard co-authors, Gütlich, Bill, Trautwein, the entire book is about Mossbauer spectroscopy. There is in this book here a chapter written by Eckhard Munk, who has given these lectures in the past 2 times at our workshop. And this is a really good chapter. I recommend that as a good introduction. There are other review articles, and I think some of them are on the Dropbox. So I'm going through, this is the outline. I'm going to tell you a little bit about a few introductory remarks about how the method was discovered and some salient features, then focus on some treatment first about the simpler quadruple doublet spectra, then the magnetically split spectra. I want to focus in particular on the correlation between EPI and Mossbauer because these 2 methods are so closely related. And then after a little bit more theoretical treatment, we'll go through a bunch of examples, and I think you will see that they are not all that frightening. So with Mossbauer spectroscopy, we are on the very high energy end of the electromagnetic spectrum. It involves gamma rays, and you see here radioactive elements indicated there. And our physicists had long speculated that it might be possible that when a radioactive isotope decays and it sends out a gamma quant, it goes from a nuclear excited state of an isotope to a nuclear ground state, that said isotope could absorb another nucleus of that isotope could absorb such a photon. And that's what the method is about. But a big problem with this is the high energy of the photon that is ejected. And people really readily realize that as the gamma photon is ejected and the propagation direction is shown here, that there will be some recoil associated with the emission of the gamma photon. And you see here the recoil energy is given by the energy without the recoil divided by this correction term where m is the mass of the nucleus. And the problem is that this recoil energy is approximately 5-6 orders of magnitude greater than the natural line width. And they are shifting in opposite directions for the absorber or the emitter and the absorber. And because the possibility of seeing such an event is proportional to the overlap, you can't see that because this recoil energy is too big. People have tried various approaches for this, and you can sort of see this in this pictorial. I'm actually not sure what this is showing. I thought this was a hidden slide. But what Mossbauer has, this is a pictorial. Well, it's a classical model where you can see what Mossbauer has shown. So if what Mossbauer has shown is that that you can overcome this recoil problem when you embed the emitting and absorbing nuclei into a solid lattice. And under those conditions, the recoil, the energy, there is a certain probability that the energy can be matched. And you see this here in this pictorial where this boat would be floating in water, and because of the recoil, as it is mobile in the water, you would not reach the target, as opposed if it would be floating in ice, there would be no recoil possible for the boat to move back on the lake to hit the object. And that is sort of the principle there. What Mossbauer has shown is that you have this recoilless absorption and emission of these gamma radiation possible if you embed the absorber and the emitter into a solid lattice. That could be just any solid sample. Doesn't have to be crystalline. It can be just amorphous, but it just has to be solid. You can't do the effect on liquids or gases. And this probability is correlated with the Mossbauer F factor, which tells you about the probability of observing this such an event. And in 1961, he was awarded the Nobel Prize for this. Since then, a lot of research has gone into this, and this is the periodic table for Mossbauer. Isotopes, the elements shown in red, you can observe the Mossbauer effect for, but the element that is clearly, or the isotope that is clearly by far the best, and is iron 57. And it is because of the nuclear properties of this. It has the appropriate energy of the excited state, and therefore the appropriate lifetime and line width that makes this possible. Right? In addition, it has a very convenient source. This is cobalt 57. And so for these reasons, iron 57 is the best isotope to do Mossbauer on. In a periodic table of life, you see the non-metal elements here in green, the metals in blue. I'm probably taking a little bit of a biased view, but iron is the structurally and mechanistically most diverse metal. And so, although the method is limited to a certain number of isotopes, it is very useful for the studies of iron-containing samples and, of course, iron-containing biomolecules. So just to summarize, so this is here the decay scheme. Cobalt 57 is radioactive. It has a half-life of 270 days. That makes it convenient. We buy a source every 15 to 18 months. It decays by K capture. It grabs an electron from the K shell, and in doing so, it goes to iron 57 in the excited state, excited nuclear state, that is, with I equals 5/2. And this then cascades down, and the transition shown in red here is the Mossbauer transition that we use as our source of the photon. As I said, this is correlated to the F factor, and at low temperatures, this is true that that all iron-containing species have approximately the same F factor, means the same extinction coefficient, so to speak. It doesn't matter what the form of the iron is. Let that be any oxidation state, iron 0, 1, 2, 3, all the way to 6, or high spin, low spin, mononuclear, dinuclear, iron in metalloproteins, iron in alloys, rocks on Earth, rocks on Mars. There are two Mossbauer spectrometers on Mars that measure the composition of rocks there, as long as it's a solid. Okay? And what's important is, because of this correlation, we can correlate the fraction of a given iron species in a sample to the area of that Mossbauer subspectrum that we observe. Okay, you'll see this later on in the examples how this works. Now, at this point, we have a photon of a single well-defined wavelength, and that is the same as you have a UV visible spectrometer, and you want to record a UV visible spectrum, and you have a lamp that shines at 800 nanometers. But you want to scan the entire range, and you do this in Mossbauer spectroscopy. We do go through a range of energies by applying the Doppler effect to the source. And in doing so, you modulate based on this equation where v is the speed with which you vibrate the source back and forth, and c is the speed of light, and E is the photon energy, 14.4 keV. You modulate the energy. And you span a tiny band of energies, and this tiny band of energies then translates into this range here where you see in Mossbauer spectra. We typically show on the x-axis Doppler velocity. It's a very bizarre, unusual way of depicting energy. And you see this here, the correlation, how you calculate this back. Of course, it is related to energy changes. We're doing spectroscopy. We're always concerned with energy changes. We can convert this back, this scale from millimeters per second, into electron volts, megahertz, wave numbers, kelvins, whatever people report this. Okay? This is what the experimental setup looks like in our lab. We have this velocity transducer that vibrates the sample in a very well-defined fashion back and forth, shines it through the sample held in this duotale at low temperature. You see here the detector. The small little opening here is where these fly in. And then the Mossbauer experiment really is a coordinate or synchronized motion of the source to the synchronized to the counting of the photons, and that's what the spectrum then looks like. So you know at any time at what Doppler velocity your source is, and you just count the number of photons flying in your detector, and some of them may be absorbed by your iron 57 containing sample that you have in the beam there. In a very similar way as you do UV visible spectroscopy, a certain fraction of the beam can be absorbed, and you measure what's coming into the detector there. Okay? There is also a small little magnet box on there, and there will be lots of magnetic field plots later on this talk, and you will understand in a few slides why we have this. We record many, but not all spectra with a small magnetic field. Some of them, we actually use a large magnetic field. This is our high field duo. It has a supraconducting magnet down here, and this actually has a vertical drive. This is the view up the top. I'm not sure whether you can see this well here. This is the velocity transducer. The sample hangs and the source hang down here. And if we lower this into the cryostat, this is then down there, and the detector box is underneath. You see this here. This is the schematic of our cryostat. The source is down here. The direction of the source is given with the red arrow. The direction of the magnetic field is given by the blue arrow. So in this geometry, by definition, the direction of the gamma beam is parallel to that of the magnetic field. There's a different type of setup. That is one that Eckhard Bill uses in Mülheim, where you have a horizontal drive. So you have the source here, and you can shine this through, and you have your detector box here. But if you take a look from the top, you can actually mount your source and detector either parallel or perpendicular to your magnetic field, and that allows you to collect different spectra, and you will see that that can be a useful thing later on. So let's talk about some spectra first. Quadrupole doublet spectra. So this depicts the energy levels of the source relative to those of the iron 57 absorber. And you can see that under the application of an electric field gradient, that the I equals 3/2 excited state can actually split into the m sub I plus minus 1/2 and 3 half states. They had a different energy here, and this is due to the so-called quadrupolar splitting. And you see here this energy, this arrow is shorter, this one is longer, this arrow corresponds to this line, this arrow corresponds to this line, because more positive Doppler velocities mean greater energies. Okay? And a quadruple doublet is characterized by 2 parameters, delta EQ, the quadruple splitting parameter, which is the separation between the 2 lines, and the isomer shift delta, which is the average position between the 2 lines. Now, what's really unique about Mossbauer spectroscopy is this separation here. If this is 1 meter, the question is, what is actually the length of these arrows if we would draw them to scale? This method has a very large delta E over E ratio. If this would be 1 meter, this separation here by 2 millimeters per second, if that would correspond to 1 meter, then the length of these arrows should be 150 million kilometers, and that is the distance Earth to Sun. What this means is, and because one thing I have not mentioned is this tiny energy band that we use running spectra from -12 to +12 millimeters per second, all different chemical forms of iron 0 through 6, high spin, low spin, mononuclear, dinuclear, rocks, alloys, everything absorbs in that range. That means we have that would mean we have the ability with this technique to read this screen at the distance Earth-Sun and be able to differentiate whether we are here, 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 or here. And with that, I think that's a very impressive technique. The caveat with this is that what we have to read is not necessarily good fine print to read. It is overlapping spectrum because we look at each and every iron species that is labeled with iron 57. They are all contributing and often overlapping, and the writing is about of the quality of a 3-year-old toddler who writes, "Mommy, I love you." And you got to spend some effort to decipher that, and if you do so, you can. Let me tell you a little bit about these 2 fundamental parameters, the isomer shift and the quadruple splitting. The isomer shift is the product of 2 terms. One is that we are in red here. These involves the electron density at the nucleus, and this is something that really varies from molecule to molecule because it conveys chemical information. This is the electron density at the nucleus. It also contains a bunch of fundamental constants. These are properties of the iron 57 nucleus, and they are the same for all iron-containing species. Importantly, there is this ratio delta R over R, the change in radius between the ground and nuclear excited state, and that is negative for iron 57. So, because it's a nuclear technique, we need to look at the electron density at the nucleus, and that's what's given here. But of course, as we all know, only s electrons have a non-zero probability at the nucleus. But the s electron density is affected by many properties, such as the d electron count of different oxidation states of iron via shielding. And I show here a couple of these radial distribution functions for the various orbitals. You have the 1s, 2s, 3s here, the 3d here, and you see the 4s here as well. And you see that these higher core s orbitals actually have quite a bit of electron density out here that can be shielded if you have different d electron counts. Now, there are tables, and this one is from a slide that Eckhart sent me that is adapted from what he has published in his book, and that goes back to another book from the early 70s. You see here that there is typical ranges for different oxidation and spin states of the iron, and importantly, there's quite a bit of overlap and ambiguity here. But if we pair this type of information up with quadruple splitting informations and measurements in magnetic fields, we can almost always understand this and assign those, despite the fact that these ranges are very overlapping. I should point out there is this range here, iron 2, high spin. This has a very characteristic range, and we can use that often to unambiguously assign a certain fraction of a species to high spin ferrous. There are some very useful trends to look for the how isomer shifts compare going from one compound to another one. And for example, as you increase the d electron count in going from iron 4, d4, to iron 3, d5, to iron 6, d6, the number of d electron increases, the capability of shielding the s electron increases, the s electron density decreases, and delta increases, the isomer shift increases, because this term delta r times r in the end switches it around. You can make similar arguments that low spin complexes have lower isomer shifts than high spin complexes. And that is because they have shorter, more covalent bonds. The d electrons are more efficiently delocalized into the bonds. They shield less effectively, and the argument goes the other way. Delta decreases. Likewise, the isomer shift of sulfur ligands is smaller than that of nitrogen-oxygen ligands. Again, the bond is more covalent. Tetrahedral complexes have more covalent bonds than octahedral complexes. Now, the second parameter is the electric field gray, or is the quadrupole splitting. It is caused by the fact that nuclei with I=1 half, such as the I=3 half excited state of the iron 57 nucleus, have a quadrupole moment, Q. And if you have an electric field gradient at the location of the nucleus, you can then have different orientations or different energies for the various orientations that are allowed for the 4 m sub I states of these nuclear levels. There's a pictorial of this. If you now have point charges, positive and negative point charges in a two-dimensional plot here around a nucleus with a quadrupole moment shown like this. This here is less favorable because there is more repulsion with the positive charges than with the negative charges, as opposed to this one where you have a greater attraction here to the negative charges than the repulsion with the positive charges, according to this orientation there. This can be quantified in the following way. This is due to the asymmetric electronic charge distribution around this nucleus. This is given by this EFG, electric field gradient. It has 3 principal components. They are labeled VXX, VYY, VZZ. The main component is usually given as VZZ. The asymmetry parameter is called eta, and it is defined as the difference between VXX and VYY divided by VZZ. Mathematically, you can treat this in the following way, in a spin Hamiltonian fashion, and this is the exact same spin operator physics that goes on there as with the zero field splitting interaction. It's a totally different physical origin, but it is the same way of using spin physics there. So it's a way, the spin Hamiltonian concept is a way to model these effects mathematically, and the way this works is very similar. And you recall yesterday from Art van der Esch's lecture, rhombicity is between 0 and 1/3. Here it is between 0 and 1, and it's just because there is a factor of 3 somewhere in there. Okay? I should point out that the observable, the delta EQ, is related through a bunch of fundamental constants here to the VZZ. Okay? There is a simple, or rather simple model where you can then relate the components of VXX, VYY, and VZZ to different orbitals that contain an electron. And of course, because the electrons are in d orbitals, this is an asymmetric distribution around the nucleus. You can see that there are different components to this. This is a very simple, yet often useful method to depict or to look at trends for the magnitude of quadrupole splitting constants. And this is just a table that is adapted from the chapter in Eckhard Münk's book. And I should point out, in addition to these rather qualitative trends, there was a great advance made by Frank Nese and co-workers about 15 years ago. Probably started a lot earlier than that. And he pioneered the field by calculating, using density functional theory methods, spectroscopic parameters, and in this case also the isomer shift and quadrupole splitting parameter. And then you can calculate for a hypothetical model structure the spectroscopic parameters, and you can then compare the experimentally observed parameters and see whether that is in accordance with the structure that you assume. You can calibrate those methods with compounds of exactly known composition and structure, and electronic structure and geometric structure. And then you can apply that method to things that you don't know the structure of, reaction intermediates and such. Okay? So on to the next topic, magnetically split spectra. I equals 3/2, I equals 1/2. After these talks that we had already heard yesterday and today, that you recognize they are magnetic, and inside them, if they experience a magnetic field, the levels will be split into the plus minus 1/2 and plus minus 3/2. We assume that there is no quadrupolar interaction here. And I'm not sure why the G values are not shown, but please note that the nuclear G values in the ground state and the excited state are different, and for that reason you have a different ordering. It's just nuclear properties. Okay, and then you can have these 6 transitions between the minus 1/2 and minus 3/2 all the way to the plus 1/2 to the plus 3/2 state. You see that this is the shortest arrow, this is the leftmost line, this is the longest arrow, this is the rightmost line at highest energy, and you can see that we can correlate the width of the spectrum to the magnitude of the magnetic field. If we would assume there is a stronger magnetic field, that would correspondingly lower this level even more, raise this even more, lower this even more, and so on and so forth, and raise this even more, so that the lines drift far apart even more. Okay? The selection rules for Mossbauer spectroscopy, it's magnetic dipole spectroscopy, are 0 and plus minus 1. The intensity of the delta M equals plus minus 1 lines is proportional to 1 plus cosine square theta. That of the delta M equals 0 lines, shown in red here now, is proportional to sine square theta, where theta is the angle between the propagation direction of the gamma photon and the magnetic field. And you see now that if they are parallel, this would be this spectrum, the sine square argument goes to 0, and the delta M equals 0 lines have no transition probability. You maximize their intensity once you're exactly perpendicular, then this argument is maximized and this is smallest. And so then you have these characteristic patterns that you can use to define what is the orientation of the magnetic field felt by the nucleus relative to the gamma beam. You notice that I'm talking about the effective magnetic field here, and that is going to play a very important role because we have, as in all paramagnetic resonance spectroscopies, we have our lab magnetic field and the magnetic field, the internal field, caused by the electronic structure of the compound we are studying. We can also have a powder spectrum, and that's when you have an orientation average spectrum, and then you have this intensity ratio. This is just to show you, in real life, you can have combinations, and you can see if you have a quadrupolar interaction, this will be a splitting due to the quadrupole interaction, and then you turn on a magnetic field, and in this very simple picture, which is in most cases, or in many cases, far from reality, probably most cases, you see that the inner 4 lines are shifted relative to the outer 2 lines, and you see that because the outer 2 lines go into the states that have delta M, have an M sub I of plus minus 3/2. Those are the ones that were raised by the quadrupolar interaction. and those into the plus minus 1/2 are the ones that are lower in energy. So that's why that's why these 4 lines, these 4 transitions into the plus minus 1/2 are lower relative to those of the plus minus 3/2. Now, as I said, these internal fields are caused by, or these effective fields at the iron nucleus are caused by internal fields, and this in turn is caused by unpaired electrons of the iron. If you just go through this collection of typical oxidation and spin states, you see that all but one actually has unpaired electrons, and those unpaired electrons are moving charges that generate you magnetic fields, and those fields are the ones that you sense in your Mossbauer experiment. So now we need to understand a little more quantitatively how we can connect EPR spectroscopy and Mossbauer spectroscopy, because these 2 methods really go hand in hand. And the reason is that you can use the exact same theoretical framework, the spin Hamiltonian formalism, to describe both types of spectra. For EPR spectroscopy, you have seen yesterday from Art's talk, the relevant terms are the electron-Zeeman interaction, the zero-field splitting interaction, which can be rewritten as this term here, where you have the axial zero-field splitting parameter D, the rhombicity parameter E, and then you have the hyperfine interaction here as well. Of course, D tells you, in a nutshell, how different the Z direction is from the XY plane, and E tells you how different the X and Y orientations are within the XY plane. And the ratio E by D, E over D, is known as rhombicity. You have seen some of the rhombograms. You'll see a few more. E over D can take values between 0 and 1/3. I mentioned it. Art mentioned it. And for those things, you have these rhombograms. Now, for EPR, and we had a bunch of spin states there, we got to now strictly separate half-integer states from integer spin states, because they are fundamentally different. Half-integer spin states have an odd number of unpaired electrons. They have s equals 1/2, 3/2, 5/2, and so on, with 1, 3, 5, and so on unpaired electrons, as opposed to integer spin states with s equals 0, 1, 2, 3, with 0, 2, 4, 6, and so on unpaired electrons. These half-integer spin states are typically EPR active. These integer spin states are, in most cases perhaps, EPR silent. There are, of course, exceptions, and I refer you, and I'll show this more explicitly on a later slide, to the talk by Eckhard Munk from 2 and 4 years ago, in addition to a chapter that was written by Michael Hendrich, but I'm not going into these details here. You see now here the difference. Half-integer spin states, and you can use a theorem known as Kramer's theorem, that a half-integer spin system is also known as a Kramer system. It always splits into sets of doublets that are known as Kramer's doublets, and under no circumstances is it possible to lift the degeneracy of the 2 states that comprise a Kramer's level, a Kramer's doublet, in zero field. That means in zero field, there is always a degeneracy of 2. It can be more if the zero field parameters are a little bit odd, but under no circumstances will you be able to lift the degeneracy of those 2 states here. And as you then apply the Zeeman effect, one state is lowered in energy, one is raised in energy, and then if the energy difference matches, you see your photon here. Your photon energy photon can be absorbed, and you can see the transition in EPR. You've heard about that yesterday. Conversely, in integer spin systems, this would be s equals 1, calculated for a not so outlandish set of zero-field parameters. This would be here the same X-band photons. You see how they sort of hang loose in between there, and at no magnetic field strength, they are able to connect the 2 states, and for that reason, many of these integer spin systems do not show an EPR signal. You can also see here already a key difference, and I'll point this out already, these two states, they split symmetrically, and they have a slope different from zero here, right here in small fields, whereas these very often bend very gently towards zero, like this one here, and they come in with a slope of zero, and that's going to be important. Yeah? Rhombograms. So you've seen them from art yesterday. Everything is contained within looking at and calculating, like for this S equals 5 system, the Hamiltonian with the Zeeman energy and the zero field energy. Our matrix size is 6. We have 6 states, and that means we have 3 Kramers doublets. 6 states, 3 doublets, each one has 2 states. And if we assume that the zero field splitting is large compared to the Zeeman, that means that these energy offsets here between the doublets is larger than the magnetic field here. Then these states split linearly. The slope is linear. They split symmetrically, but in a very odd and unintuitive fashion. You see this here. The splitting is dependent on the orientation of the magnetic field. The splitting is dependent on what doublet you're looking at. And what these rhombograms do is they connect the effective G values, and I point out these are effective G values, not real G values. Effective G values because we now in this perturbative treatment say we look at each Kramers doublet one at a time and treat it as an effective S equal 1/2 system. Why 1/2? Because a 1/2 system has 2 states, the 2 states of the Kramers doublet. And then we take a look, how do the 2 states split under the application of a magnetic field? If it is like this, if this is a splitting, how an unpaired electron, a free unpaired electron would split, we call this a G of 2, an effective G of 2. And we find this now calculated for D of 2 and an E over D of 0. So we are on our rhombogram here on the very left axis. We see that for the ground doublet in the Z direction, we are at 2. For the ground doublet in the X and Y direction, we are at 6. And we should be both at 6 because X equals Y by definition of E over D equals 0. The XY plane is isotropic there, but different from the Z direction. And we can do this for the other ones as well. You see here for the middle Kramers doublets values of 0, 0, and 6. The fact that these go out here has to do with the fact that the electron Zeeman now starts competing, and this condition is no longer fulfilled. But here, the 2 states have a slope of 0, and they don't open up. But here in the Z direction, it has a slope of 6. So 6, 0, 0. And conversely, we have 0, 0, 10 for the upper Kramers doublet. If we now look at the fully rhombic case, we are now looking at the right side of the axis. We see for the ground doublet one large value, effective G of 9.6, and the other 2 are very small. For the middle Kramers doublet, you see that all 3 come together in one point, and that means the splitting is independent of the molecular orientation. It's the same for the X and the Y and the Z direction, for all directions in between. And for the upper doublet, you actually have the large G value of 9.6, and then the other 2 are 0.9 and 0.6. And actually for E over D of the fully rhombic case, the sign of D is not defined. You will see that the Y and Z axes are just interchanged. You can just, a flip of the sign of D is just correlated to a relabeling of the axes there. Now, how can you do this, use this to construct EPR spectra? You do this by following this algorithm that you've seen before, where you can have the limiting case here with 3 different G values. You have your 3 G values here. You plug this in here to this equation. You can read this off the field. The effective G value is inversely proportional to the field. Higher G values occur at lower magnetic fields. Because higher G value means larger splitting of the states, you need a correspondingly smaller magnetic field to reach the resonance condition. Example. This is a non-junk iron, high-spin ferric. This is protocatechol 3,4-dioxygenase. This has an intense 4.3 signal. We are here in the rhombic limit. This is caused by this Kramer's doublet. All molecular orientations have the same effective G value. They all absorb like this here. They all, if you integrate this, this is one big absorption-like signal. Okay? If you tune in here and blow this up by a factor of 50, you'll see that there is a peak. It is coming from you can measure the effective G value in the Y direction here. Okay? So I hope you see that these rhombograms can be useful. These rhombograms can also be useful in real life. Okay? Yesterday, we said farewell to Susan. Susan will leave our group. We went to Herwig's. And afterwards, we went to the bar. And at the bar, I found out something shocking. I heard that some person ordered a Wiener Schnitzel and anticipated a bratwurst-shaped piece of meat. And this would not have happened. This is not really acceptable, but or it's the wrong expectation. And you can really overcome this with the proper use of rhombograms. The Wiener Schnitzel is clearly, where's the Wiener Schnitzel? The Wiener Schnitzel is here. It is axial 6, 6, and 2. Okay? Where's the bratwurst? Well, the bratwurst here is like fully rhombic. We have a fully rhombic. No, here, the fully rhombic, large G by. You see this here. We see other things in here. Knödel, a meatless thing, isotropic. You pretty much find the junk knödel on pretty much every other plate at Herwig's, and they are pretty good, by the way. So what's the take-home message? If you don't know the rhombograms, the expectation value for schnitzel is not a bratwurst, really not. So, now that everyone's awake, we continue with the stuff. How does this connect? For Mossbauer spectroscopy, we use the following Hamiltonian. The following terms need to be considered. The electron Zeeman, the zero-field splitting, the hyperfine interaction, the nuclear Zeeman, and the quadrupole splitting. And you see, now Mossbauer is a nuclear technique, and only we need to calculate the nuclear levels. But you see, if they are now ordered according to, rank ordered according to strength of the interaction. I mentioned to you that we put a small magnetic field, and the reason we do this is when we put a small magnetic field, this term and this term, they are both much larger than the hyperfine interaction, and that itself is also larger than those two. Then we can use perturbative treatment, and that is we calculate these two first and ignore the hyperfine coupling, and that is under those conditions a valid approach. What we do then is, after calculating this and knowing the electronic structure, we calculate what's known as the spin expectation value. You put the spin operators in between your real wave function that come out of this treatment, and we replace the spin expectation value in the hyperfine term, and now the spin expectation value contains all the information of the electronic structure here. Yeah? And then in the next step, we look at the nuclear levels. In part 2 of the calculations, we look at the nuclear levels. This is our quadrupolar interaction. This is our nuclear Zeeman. This is our hyperfine. And what we then do is we calculate this. We rearrange it a little bit. And you see that all these terms have now here, these two terms have a similar dependency in shape. When we rearrange this and divide this term by the nuclear G factor and the nuclear magneton, we can then lump these two together. And you see that this term, hyperfine divided by G and beta n, takes the units of a magnetic field. And of course, the magnetic field, the internal field and the external field is additive. What we measure in a Mossbauer experiment is the effective field at the nucleus. The external field we know. And what we then can back out from this is the internal field. The internal field is dominated by S and A. And from that we can back out our electronic structure. So that's the flow of logic, how we can use magnetic Mossbauer spectra to pull something out of, learn something about the electronic structure. So this is the internal field here, depends on S and A. Just briefly, you find this, and we have heard it before. A has several components. The Fermi contact shift is the predominant one. It is caused by the polarization of the core S electrons by the, shown here, spin-up electron. The spin-up electron likes to hang out more, on average, more often to close to the d electron, and conversely, that then leaves a more net spin-down density at the nucleus, which can be felt, and for that reason, because there is the spin-down density, it is negative. The effect is isotropic because it involves an s electron, and for iron, it gives typical values of -20 to -22 Tesla. Other contributions to A include the dipole contribution and the orbital contribution. You already heard about those. They arise from the fact that electrons are in orbitals that are not spherically symmetric, and that those orbitals can have an unquenched orbital momentum. Now, the spin expectation values, the other thing that defines the effective field, are given by, they are proportional to the slope of the energies, the states, energy of the states with respect to the magnetic field, and you can show that the expectation value is approximately the effective G value divided by 4. And that's the correlation between EPR and Mossbauer. Now, what's important is to realize, because the spin expectation value of each state is related to the slope, so each state has an expectation value. And what we'll do now is do this in 2 steps. We first will look at the expectation value of selected individual states. What do the Mossbauer spectra of those states look like? And then we need to consider that the system is not just in one electronic state, and that there may be and that it's fluctuating through all kinds of different electronic states. And that's the second step. Yeah. So, expectation value of something simple, s equals 1/2. The slope is given, and it's proportional to the m sub s value. So the red state here has an expectation value of -1/2. The blue state here has an expectation value of +1/2. And this one is essentially isotropic, meaning the same for all 3 directions. Now, for s equals 5/2 case, we go back to the energy diagrams that you have already seen. I show the effective G values here. Now, keep in mind that the effective G value is correlated of how rapidly or how strong, under the application of a magnetic field, the 2 states split up. And that, of course, is directly correlated to the slope. And that's why the 2 are so correlated. And you see now here, for the ground doublet, this is the other states. I'm not sure whether you can see this. Always the lowest state here. This one is the steepest, y direction here. And the x and z direction are conversely much less. So we have an expectation value that has a very strong component in the y direction, but not x and z. And the other example would be the isotropic case, the 4.3 doublet, where it's the same for all 3. And in EPR, we see that always the signal occurs at the same position, and that is because the states always split with the same slopes, and of course, for that reason, the expectation value of those states is always the same, this isotropic. Now, for non-Kramer systems, now s equals 2, this is very different. I mentioned to you, this is now calculated for a system with s equals 2, with a d of 10 and a rhombicity parameter of 1/3, just arbitrarily chosen. And you see the 5 states here, and you see they depend on the x, y, and z direction qualitatively. You see also that each and every state comes in with a slope of 0 into the magnetic field of 0. And for that reason, they have no slope at 0. And for that reason, they all start out at 0. And that is important because that means an S of 0 times an A that is non-zero means it is still 0. And that means there is no magnetic field, no internal field for the Kramer systems in many cases, not all cases, in small magnetic fields. So if we have our matrix, EPR versus Mossbauer, and half integer versus integer spin, those here are EPR active. Those are, for simplicity, considered EPR silent. In small external fields, they have essentially a small, maybe no internal field. That depends on the constellation of zero-field parameters. And here we have sizable internal fields because they have the full expectation value, even in the smallest possible field. And now we need to understand how these are oriented. I'm just having a depiction of a molecule here. You see the anisotropy. This will be the depiction of the expectation value. If something would be high-spin ferric, this would be the middle Kramers doublet. This would be the ground Kramers doublet. We now consider two cases. One is we have an isotropic case, an isotropic expectation value. If our external field is oriented like this, parallel to the gamma beam, now our internal expectation values, our internal field can align perfectly anti-parallel. This is the quantization axis here, and you see that under those conditions, we have that each of the molecules can have its internal magnetic field aligned anti-parallel to the external field. Under those conditions, the delta M equals 0 lines vanish, and now we do our trick and just move our magnet box by 90 degrees, and then the external field is just rotated by 90 degrees relative to the gamma beam. And now, because the expectation value is isotropic, now the quantization direction is still given by the external field, and now the delta M equals 0 lines are here. And what is the consequence? When we have something isotropic, when things are really intense in the EPR, because then all the resonance positions come together at the same magnetic field. And under those conditions, once it is really isotropic, we can direct all the internal fields by just having a small external field. So whenever you have very intense EPR signals, one has this, you can then see this field orientation depends. On the other hand, if you then have these very anisotropic spin expectation values, irrespective of whether your external field is like this or like this, the magnetic quantization axis is given by the direction of the internal field. So you try to light up you have this, the orientation of the external field, and you maximize the component along that, but then you see that the maximum component comes with other components that are defined by this very anisotropic expectation value. And as a consequence, if you have a sample that is randomly frozen, you then have random orientation of the expectation values, and you have a random orientation of the internal fields, and at that point, you have your powder pattern EPR Mossbauer spectrum. We need to now consider that for paramagnetic systems, the system has more than one state. By definition, if it has one state, it's diamagnetic. We can hit that pretty easily. And we now need to consider the fluctuation rate between the electronic states relative to the time scale of Mossbauer spectroscopy. That's defined by the lifetime of the excited nuclear state and the Larmor frequency. And there are three cases, and as always, there is two limiting cases that make it easy, and one case where they are similar, it's in the middle. Case one is the relaxation between the electron states is slow, and I show this on the next slide, and that is often encountered, but not always, for metalloproteins at low temperature. The other case would be that the relaxation between the electronic states is fast, and that we encounter at high temperatures. And again, high is not really a quantifiable term here. Oftentimes, 30 Kelvin suffices. Sometimes you've got to go to 120 Kelvin, and it is still either here or there. So each case is different, but you have ways to diagnose it, and I personally just try to avoid it. The simulation software doesn't easily do this, and it's much easier to deal with these, in my personal view. But that's a personal view. the slow relaxation limit. Consider the following case. You have these molecules here. So there are two states, and they have a certain expectation value, and you now have the red state. The molecule during the time of the Mossbauer event, these 7 red molecules stay in the red state, and what the Mossbauer spectrum, what you see in the Mossbauer spectrum is the expectation value that is characterized by the red state. Conversely, the other molecules here, they stay in the blue state, and of course under longer times they don't. Everything fluctuates and it changes. But the question is relative to the Mossbauer timescale. On the timescale of Mossbauer, these 7 stay in the blue state and experience the blue state, and these 7 experience the red state. And what you then do is you calculate the Mossbauer spectrum for this state and then for this state, and you calculate and you superimpose. Your experimental Mossbauer spectrum is the superposition, Boltzmann weighted superposition of these 2 doublets. And if you are at a large magnetic field, this could be something like 80-20. If you are at a small magnetic field, they are equally populated, essentially. Yeah? Now, conversely, in the fast relaxation limit, now the molecules jumble up and down fast on the timescale of Mossbauer, indicated here by the average color, purple. So they experience during the Mossbauer transition both this state and that state. What you do is you calculate the average expectation value from the Boltzmann factors and the individual expectation values, and then your Mossbauer spectrum is one subspectrum with this Boltzmann averaged expectation value. Now here's an important consequence, and that is in a small magnetic field, even if you have a system that is half integer, let's say s equals 1/2, like this, and the internal field is large. The internal field is on the order of something like 40, 50, 60 Tesla. You have magnetic spectra that are split like this, and you have all the mess of all the terms of the Hamiltonian in there. If you go to high enough temperature, you now are really in this situation where the energy difference is very small. They do have expectation value, the full expectation value, but the number of molecules that has the red expectation value equals the number of molecules in the blue expectation value, and because the states split symmetrically, the Boltzmann averaged expectation value is 0, and under those conditions, with S equals 0, the internal field vanishes, and your messy magnetic spectra collapse into quadrupole doublets, and you get those fundamental parameters from those spectra. Okay. When is S equals 0? Something to strive for simplicity. Diamagnetic compounds have no expectation value, no internal field, quadrupole doublet. Paramagnetic compounds with an integer spin ground state. Remember that these states, they go into with a slope of 0 in many cases towards the magnetic field of 0, and for that reason have essentially or have often a small magnetic field. And collapse to quadrupole doublets, and compounds in the fast relaxation limit as I just described it. So, where that then leaves us with our matrix is here. EPR species, hyperactive species have a half integer spin ground state species are EPR active. They can be isotropic, S equal 1/2, or anisotropic, S equal 5/2, ground doublet, middle doublet. You've heard it. You can look at those. You get, at low temperature, when the relaxation is slow, for those systems, because they have a large expectation value in small fields, and because the fluctuation rate is slow, for those spectra you get magnetically split, and they can be a mess. Okay? What challenging. I like them. At high temperature, in small magnetic field, things collapse to a quadrupole doublet. And so these two then provide you with complementary information, plus from the EPR, we know what the zero field splitting parameter is, we know what the spin state is, and we can feed all this information into the analysis of the Mossbauer spectra because we have about sometimes 10, 12, 15, 18 parameters that we can turn knobs on, and so we can fix some of them. Okay? Conversely, integer spin species, as I pointed out, often EPR silent, not always, but those that are typically exhibit quadrupole doublets in small magnetic fields, and they give quadrupole doublets in small magnetic fields, but as you increase the magnetic field, you start saturating in these expectation values. This is actually on this slide back here. You see this here shown from 0 to 8 Tesla. This is accessible with the magnetic field in the on a dual high field duo. We start out here, our low field spectra are here, no expectation value, quadrupole doublets, but as we then turn on the magnetic field, we can now really probe what the expectation value is as a function of the external field. So we measure the internal field as a function of the external field, and that's your electronic structure. Okay? A few examples. Transferrin, a high-spin monoferric site. EPR shows this. You see something centered roughly at 4.3, not quite, a little bit split. You see here, this gives rise to these three resonances. You see that the three effective G values are separated a little bit. This is reported as having an E over D of roughly 0.3. What do we expect for the Mossbauer? Well, you know, that's actually pretty much a mess. If you look at it, you know, it would scare me away. And when I saw similar spectra for the first time in 1995, when Eckert showed them to me, I was pretty lost. Let me walk you through those. These spectra are in the slow relaxation limit, and we show here spectra in a magnetic field of 50 millitesla parallel and perpendicular, and then we increase the magnetic field to half Tesla, 2 Tesla, 6 Tesla. You see, these are the parameters, and you've seen what the zero field parameters, what the effective G values are from the previous one. You see here in this garden variety of states that we need to consider now all the contributions from the different Kramers doublets. D is small, 0.25, and at 4.2 Kelvin, these are already appreciably populated. If you now plot the three spectra of the three doublets, you see this here would be the lowest doublet. This would be this one here. The splitting is big. The intensity ratio is 3 to 2 to 1, 1 to 2 to 3. Why is it like that? Because we have a magnetic uniaxial spectrum. Now those conditions, we are here. This is our large G value. Those are our small G values. Our external field can't do anything about the orientation, whether we go parallel or perpendicular, not indicated here, but parallel and perpendicular give you the same spectrum. Same for the highest doublet. You see the splitting here, and it is correspondingly the large G value, which is now along the Z-axis. Okay? Middle Kramers doublet. Splitting that is field dependent, field orientation dependent. 3 to 0 to 1 to 1 to 0 to 3, 3, 4, 1, 1, 4, 3. The splitting is only half. Why is the splitting only half? In this case, the magnitude of this splitting represents our effective G value of 4.3. Okay? And let's just assume for simplicity, and that's true for high-spin ferric, because the hyperfine tensor is isotropic, essentially. For the other two doublets, the splitting is approximately twice as large. Why is it twice as large? Because because the internal field is twice as large. We only probe for the ground doublet the Y direction, and for the excited doublet only the Z direction. But when we do probe those, they have the full expectation value, and that is about twice as much as that one. So you see this the ratio there of the outer lines reflects that. And of course, this has the field orientation dependence, as expected. We have, what I wanted to point out here is these doublets are not exactly superimposable. This is an interesting feature. Why is this? If you go back to the slide, that the inner 4 lines are shifted relative to the outer 2 lines. We are probing the y direction here. We are probing the z direction here. The field gradient has different magnitude for the y and z direction, and so the shifting of the inner versus the outer lines is different. That's what you see in there. What you also see is, as the field increases, that the lines go in, and the reason is that the internal field is the large one, is large compared to the external one. So and they are in the ground state aligned anti-parallel. So as you increase the external field, you decrease the gap and reduce the internal field. So the normal field dependence that you would anticipate for something that has the same expectation, that's an important disclaimer if you analyze. There are other cases, but for this case, as you increase the field, the lines move in because the effective field gets smaller, because the internal field remains the same, and the external field is anti-parallel. Okay, example 2. A dinuclear cluster, myoinositol oxygenase. This is an unusual enzyme because it uses an iron 2,3 cofactor, and it binds oxygen to it's proposed to bind oxygen to the iron 2 side and abstract hydrogen atom here from the substrate myoinositol molecule that is held by the Lewis acid iron 3 and pull off this hydrogen atom. Let me show you some spectra of the resting state. EPR spectrum, or what is going on with these biological ligands. High spin iron 3, high spin iron 2, S equals 5F, S equals 2. These couple antiferromagnetically. The total spin is the sum of the 2 local spins. We apply the Heisenberg-Dirac-van Vleck Hamiltonian that you find in many books. It's a fairly straightforward, easy thing to solve. The energy of a spin state given by the total spin S is J, the interaction strength, times S plus 1. And if you plot this for a positive sign here, meaning antiferromagnetic in this definition, S equal 1/2 is the ground state, and this is your spin ladder. At low temperature, you probe by EPR the S equal 1/2 ground state. That's it. Okay, so with EPR, you probe the total spin. Now, Mossbauer, local method, you have 2 distinct iron sites. One is iron 3, one is iron 2. You go to high temperature. Although you have, this is S equal 1/2, this thing has an expectation value. You go to high enough temperature, it fluctuates fast. Thermal average of the expectation value is 0, no internal field. These are your 2 quadrupole doublets. These parameters here of the red doublet are typical of high spin iron 2. These parameters are typical of high spin iron 3. So we get the intrinsic iron oxidation state out of this, and we can now use these parameters and fix them for the subsequent analysis. Low temperature, the system is in the slow relaxation regime. Expectation value is minus 1/2 for the ground state, plus 1/2 for the excited state. And what you see is these magnetically split spectra. And you see the 2 sides. Blue is iron 3, red is iron 2. Again, you have 2 distinct iron sites. You see them both. S equal 1/2, isotropic. Remind you here, for any sort of Mossbauer analysis, although there is a little bit of anisotropy in here, but this is really if you take your soccer ball and squeeze it by 5% in this direction, and it's still isotropic for the argument of the field orientation dependence. And because you have this rather intense EPR signal, you have these strongly field orientation dependent spectra. And that is exactly what you see. You can record parallel, perpendicular, and the difference spectrum then nicely reflects the line positions that you can obtain from that. What we can learn from spectra collected in magnetic fields is something more about the spin coupling scheme. The reason is, so Mossbauer is a local method, and it's what really matters is the hyperfine interaction. The hyperfine interaction with site 1 and at site 2. It's really between the local spins of spin 1 with site 1 and of spin 2 at spin 2. But when we do this calculation, we have our spin ladder. We do calculations often with, so the S equal 1/2 ground state. That is a good spin quantum number, provided that this coupling is strong. And that means that the relative orientation of those two spin arrows, representing the ferric and ferrous side, are at a fixed orientation, and this is the S equal 1/2. So EPR probes the total spin of this, and Mossbauer looks at the two sides individually. What we need to do is try to find out how do the individual spins contribute to the total spin. This is given by the spin projection factors. You can find this in books like Gatteschi and Bencini. Other books, it's straightforward to write out. And you can then replace the local spins, S1 and S2, with a total spin, like 1/2 for the ground state, times this projection factors. And they are +7/3 for the Rn3 side and -4/3 for the Rn2 side. They always add up to 1. And importantly, they have a different sign. And the different sign means that that this essentially in a nutshell means the Rn3 spin is parallel to the total spin, and this one is anti-parallel to the total spin. And now when we look at field-dependent spectra, this argument that I just mentioned to you is sort of turned on the head, where I said as the field increases, the lines move inwards. That is true for the site that has the positive spin projection factor. You see this here, the iron, we go from 3 Tesla to 6 Tesla to 8 Tesla. The Rn3 spectrum is in blue. You see the lines move inwards. And if you follow this line, blue line, further inwards. And likewise, you see this here. Yeah? For the Rn2, you see this opposite behavior. And the reason, you see this here going from 3 to 6 to 8, you can nicely track those. And the reason is the Rn2 side is now anti-parallel to the effective field. So as you increase the total field there. This is all true for the ground state. For the excited state, it's the other way around, because the sign of the expectation value changes. You see here the excited state. This is the excited state of the Rn3. This is the excited state of the Rn3. This is how you go from 3 Tesla to 6 Tesla to 8 Tesla. Your expectation value remains the same. It's S equals 1/2. What changes at the same temperature is the population difference. You go from something like, say, 60-40 to 70-30 to 80-20 because the gap increases as you slide down the field. Okay? The Mossbauer spectrum is the superposition according to their Boltzmann factors, and you see now that this here is more intense than this and more intense than that. Okay? These lines, I'm not showing it here, but these move out because the expectation value has the opposite sign. So for the excited state, the lines move outwards, and of the majority spin and of the minority spin, they move inwards. The Rn3-3 cluster, now it's getting simple. Ribonucleotide reductase, no more spin Hamiltonians, I promise. Do I? Almost. Okay, the Rn3-3 cluster, ribonucleotide reductase, the active form has a tyrosine radical in the vicinity of a carboxylate bridged diferric cluster. This thing is important for ribonucleotide reductase. You can see it on many posters. I don't want to go into the details. The diiron tyrosine radical is down here. There is proton-coupled electron transfer from the R1 subunit into the R2 subunit. That's the function of the thing. You make this diiron 3 tyrosine radical cofactor by reacting the diferrous form with oxygen. You go through an intermediate, you make this tyrosine radical diiron 3 cofactor. This is what the structure of this looks like. By EPR, you see this tyrosine radical characteristic pattern. You see spin densities on those 4 atoms here. There is coupling in particular with these 2 beta hydrogens and also these 2 ring protons. There is no interaction with this diiron cluster. This diiron cluster is also is not magnetically interacting with this. This, in fact, is diiron 3 interferomagnetically coupled, S equals 5 half versus S equals 5 half, S equals 0 ground state. We see 2 quadruple doublets, 4 lines, 2 quadruple doublets. Why do we see 2 quadruple doublets? We have 2 chemically distinct iron sites, as simple as that. Every chemically distinct iron site gives its own Mossbauer spectrum. We prove, not we, it is proven that this thing has a diamagnetic ground state. This cluster was originally characterized in 1973. I want to say at Penn State, because George Lang, who is a pioneer in Mossbauer spectroscopy, was a faculty member in the physics department at Penn State, and he's on that 1973 Atkin et al. Paper. And that probably was the first time that this was reported. This is from a paper from Eckhard Munk from the mid-'80s. You see now that these quadruple doublets in a magnetic field, they split because there is a magnetic field at the nucleus, but it's only the external field. And once you can then precisely predict what this should look like. If the effective field equals the external field, then the internal field is 0, and that means at 6 Tesla, S is equals to 0. But then we are left with, how do we actually pair up these lines? We have 4 lines of equal intensity. Mathematically, we can do this. We pair up the 2 outer ones and the 2 middle ones, and this looks like, this looks high-spin ferric, like this one as well. Delta Q a little bit high, unanticipated high, both of them. The magnitude of this is due to the asymmetric binding of the oxo bridge, by the way. But, for this argument, we could also pair them up like this, and we can't distinguish from this spectrum. The parameters are probably a little bit more unusual, but one needs to always keep an open mind and think about unusual active sites, right? Now, I think this third solution is purely mathematical. This is probably 2 science papers in one. And they don't do you any good. How can you prove this? And that's when you need to think outside the box. That's when you really need collaboration with gifted biochemists who know about what the method tells you and things like that. We cannot distinguish and assign those lines here because they have all the exact same intensity, right? What would happen if they would not have the same intensity? That is exactly the question that Marty Bollinger was asking in 1997, I want to say. You now have 2 distinct iron sites at the level of the diferric tyrosine radical. Those are locked in, and you can't do much about it. But at the diferrous state, those are labile. And if now the 2 iron sites have different affinities, it might be possible to take an anaerobic solution with a substoichiometric of a green iron isotope and mix it with an oxygenated solution of a black iron isotope. And upon doing so, you hope that you have, because if this side here to the right has the greater affinity, you would then tweak it in there, that in this reaction you would favor the assignment or the distribution of species like that. That, of course, on paper looks nicely black and white, but in reality never works 100%. But we don't need 100%, in order to assign those lines. When you do this, you go from, when you preload this with a substoichiometric amount of iron 57, and then react it with iron 56, you get this. And you see now 1, 2, 3. You see 2 big lines, another resolved line, and this other one here that is the shoulder. Unambiguously, that lines 2 and 3 need to be paired up. Likewise, if you do the experiment the other way around, You preload with iron 56, then you hit it with a lot of iron 57 and oxygen, and importantly, you clean up your sample, because this thing is stable. You can clean off the excess iron 57, and if you don't, you have a broad background on this spectrum due to unspecifically bound, non-cleaned off iron 57. Mossbauer sees it all. Whether, the things you want to see, and if you don't clean the sample up, you see that as well. So that's an important step in there that needs to be considered. I think I'll do this one now, tau D. Another fairly straightforward, simple experiment to use Mossbauer spectroscopy to recharacterize this iron 4 intermediate. These enzymes activate dioxygen to reductively cleave the co-substrate into CO2 and succinate and hydroxylate this, and you have here the active site. This is the catalytic cycle. I don't want to go through the details. The key is that, well, if you go through the iron oxidation states, this is iron plus 2, integer spin, no EPR signal, Mossbauer quadrupole doublet. Same here, same here. Iron 3 superoxo, a bit messy, as we now know, but it doesn't accumulate, but also not EPR active necessarily. Predicted to be EPR silent in integer spin, a quadrupole doublet. Predicted to be EPR silent in Mossbauer quadrupole doublet. Presumably a big mess, but doesn't accumulate. And this one is a integer spin Mossbauer quadrupole doublet EPR silent. That's what's predicted. This is an enzyme that I would call is in the Mossbauer manifold. So you look at the Mossbauer spectra, high spin iron 2, the reactant complex, isomer shift of 1.16. I mentioned to you, once you see that, it is high spin ferrous. You can unambiguously assign that. Together with a fairly large delta EQ of closing into 3, because you have one extra electron in an orbital, and that orbital gives you then an expectation value to your field gradient. Something like these parameters are spot on high spin ferrous. Okay? You react this thing then with oxygen for 20 milliseconds. You see a new line here, and you can then analyze this in a very simple fashion. Now, the Mossbauer spectrum of any sample is the superposition of the various species contained in there. So what we see here is 1, 2, 3 lines. 2 lines we already know. This one is the low energy line of the ferrous. This is the high energy line of the ferrous. We noted that this line has a much greater intensity compared to this one. So you already see that that looks like a superposition of 2 quadrupole doublets. One is the ferrous here, and the other one is the new stuff that has a line here and the other line in there. If you do subtraction, and we do this in the practicals, you can unmask these parameters fairly straightforward, and you can see that this is, it was not really, therefore it's iron 4 when we originally published it. That's actually unusually high for iron 4. Again, computation by Frank Nese's group established that that is actually quite typical for iron 4 in the high-spin configuration, and this was the first, as you will see, high-spin iron 4 in a second. Now, one thing that you can do very easily with these spectra is it's a superposition of a couple of quadrupole doublets. By determining the relative area of this, you can determine what is the relative amount of that, and you can use Mossbauer spectroscopy as a kinetic method. What you plot here is the amount of this intermediate. We called it J at the time. Still do occasionally. It is in honor of J.C. Price, who discovered it 15 years ago, something like that. So you see, we know what the total iron is, and we multiply that with the fraction of the subspectrum contributed by the iron 4. If this is something like 50%, it is 0.5 times the total iron is the concentration here. So this was an experiment that was done with something like 1.4 millimolar iron. So you can back this out right away from this analysis. And then you see at 80 milliseconds and 220 milliseconds, that gets progressively smaller. And just by adjusting the area of these reference spectra, you get the kinetic information out. There is no fancy spin Hamiltonian involved in there. You don't even need a Mossbauer quadrupole doublet simulation for this one. You just compare raw spectra and you get it all out. So it's really not a method to be scared about with all the Greek alphabet soup in there. Okay? What you also see is, and it was a little bit more tricky to show, is there's a second intermediate that accumulates. We couldn't really tell that by Mossbauer easily. The information came really from stop flow and kinetics. And knowing this, you can then go back and piece this out. You see that this line reforms, and this then, the second intermediate, must be high spin ferrous. And this is indeed the case. This is this product complex here. Yeah? When you then collect spectra of this same 20 millisecond sample in a high magnetic field, you get spectra like this. How do we analyze those? We know that this is a one-to-one mixture of high spin ferrous and your iron 4. At that time, we were interested in the iron 4. And we had no intention of characterizing the iron 2, and I think I will not ever have that really. High spin iron 2, unless there's a really good reason. High spin iron 2 is very difficult to treat because it has an integer spin ground state. The expectation value gets magnetized in with the increasing magnetic field. Hyperfine tensor is anisotropic. Zero field splitting tensor is anisotropic and field dependent. The quadrupole splitting is large, and all your components are shifted by large amounts due to the field gradient components. As a consequence, these things are very tricky. They can be handled. But for our purpose, we didn't really wanted to reinvent the wheel. What we did is we took a reference spectrum of the ferrous and we scale it to 50%. Why 50%? Because we know from the low field sample, where this is nicely resolved, it's 50%. And the sample composition, of course, doesn't change as a function of the magnetic field. So we just at face value take this out. And what's left behind is then this rather beautiful 6-line spectrum. And when you analyze this with a spin Hamiltonian, well, you see that the splitting is pretty big. It's too big for a typical S=1. Mind you, the hyperfine tensor is typically minus 20, minus 22 Tesla. With that, the splitting would be too big to account for an triplet ferrule. It has to be a quintet. In a nutshell, 4 unpaired electrons give you a bigger internal field than 2. That's what this means. And so you see the splitting here. So that's really what this boils down to. We have done calculations with Frank Nese's group. I don't want to go into the details, but the Z component is not visible in those spectra. He predicted it to be much more negative. We then really measured some spectra at elevated temperatures and were able to put an upper limit on that, and it is an example where things fit nicely together. I don't want to go through this in the interest of time. It is more spin Hamiltonians, and let me go through a few sample considerations. You should have perhaps, the standard default is, I tell people, roughly 300, 400 microliters of something that's 1 millimolar iron 57. With a natural abundance of 2.2%, that means you need to enrich. It's about $4 to $5 per milligram, and if you reconstitute, that's about a 50-cent experiment, no problem. If you need to grow your bacteria on a defined source of iron 57, that is probably, Squire, how much is it? Probably a $50 experiment. Not much more than that. If you can make samples with 3 millimolar iron 57, please do so, because it really cuts down on our instrument time. Because instrument time is long, we need to collect each of these spectra for about 1 to 1.5, sometimes much longer. And we spend about $100 of helium and source costs per day. You see that the costs for iron 57 really are essentially a perturbative cost there. So, other things, Mossbauer and EPR are a dream team. If at all possible, make a parallel Mossbauer, parallel EPR sample under the exact same conditions. That's always helpful if you have an EPR signal. that helps the Mossbauer guys really with the analysis of the spectra and to reduce the complexity and to understand what's going on in the sample. You should avoid high concentrations of heavy atoms because they scatter inelastically. For people doing model chemistry, a solvent that is really not good is dichloromethane. You cannot have a thickness of more than 1 millimeter, or your beam doesn't see the end of light anymore. So I chose this picture to thank a few people. Of course, my Mossbauer advisors, Eckhard Bill and Vincent Hoen. As I said, everything I know about spin Hamiltonians, you can trace it back to Eckhard, and then also lots of discussions with Vincent. On this picture, there's a lot of people who really helped out with the Mossbauer. First and foremost, I have a long-standing joint group with Marty Bollinger, and he's thinking in Mossbauer terms and making a sample and all this. We have Mossbauer people who have analyzed Mossbauer data. Alex, who is in the audience, has his own Mossbauer lab now. Maria has her own Mossbauer lab now. And Bo has analyzed a lot of the Mossbauer data. And Bo has made a lot of the plots that I've showed you here because of the last-minute nature of this talk. I also would like to point out Bennett Stride, who is here in the audience, fourth workshop, fourth time Bennett is around. Bennett is a VIP. He has been making these schedules in 2012 and 2014. 2016, it was with Bo and Bennett that we finalized those schedules. With this, I would like to tell you a little story. Is it difficult to teach people Mossbauer? I think yes and no. Right after the last workshop, we got this cute little kitten, Leo. And at some point, he looked over my shoulder and had way too much energy. And, I'm like, Leo, you got to stop this. Let me tell you a story about something high energy. Maybe you enjoy this. And, he was reading this manuscript that Maria and I wrote. Here, The Lifetime of the Excited State. And he is excited about this. And he wanted to get into this. He actually cross-checked the poster. And, this is IPNS. And, I'm not sure how much we actually owe Leo to that this thing finally has the scene of light. And he's actually clearly thinking about this. And, I'm not. So the other cat we have is Lefty. Lefty is a very, very sweet cat, but our Mossbauer training efforts did not work out that well. Lefty was thoroughly unimpressed. Here she is sleeping, and after all this, she's thinking, Mossbauer? Mossbauer? She's thinking Tom and Jerry. And she incorporated various themes into her from these Mossbauer lectures. This is the random orientation of spin expectation values. This is a parallel orientation of the magnetic field with the gamma beam. But I stopped teaching her when she told me what she thought about recoilless absorption and emission of photons. And with that, I'd like to thank you for your attention. Are there any questions? Okay, maybe time for a quick coffee break and recharge and get ready for Stefan. I think we can reconvene on time.